All right, so hopefully you took a second to think about what this spring might do if you just let it run and it doesn't suffer from damping, but you do push it really hard at some point and then just let it continue on its way. Now we're going to actually find the solution, and you can see if your intuition checks out. So we're solving that y double prime plus y equal to, equal to 4 delta of t minus 2 pi, with y of 0 equal to 1 and y prime of 0 equal to 0. So this is a Laplace transform problem, so we always start by taking the Laplace transform of both sides. So we've got that L of y double prime plus y should be equal to, the Laplace transform of 4 delta of t minus 2 pi. And so that L of y double prime plus y, we can just solve the way we normally would. That gives us s squared capital Y minus s times 1 minus 0 plus capital Y. And that L of 4 delta t minus 2 pi, we found a second ago, it's 4e to the minus 2s. Sorry, 4e to the minus 2 pi s. And so from here, we want to isolate y and then sort of solve for capital Y. So I've got this s squared term times y, and I've also got a 1 times y. Okay. Here's a 1 times y from right there and right there. And then I've just got this extra minus s term equal to 4e to the minus 2 pi s. So y would be equal to 4e to the minus 2 pi s divided by s squared plus 1, plus moving this s over to the other side, s over s squared plus 1. So hopefully that checks out so far. I know I'm going kind of quicker through it, but this Laplace transform stuff, you've now been taking Laplace transforms for like 3 weeks. So, you know, hopefully we're starting to take these problems a bit more quickly. Maybe pause and make sure that you understand everything up to this point if that stuff is still a little bit unfamiliar. And then we want to go ahead and find our solution, which we get just from taking the inverse Laplace transform of capital Y. So we've got 4e to the minus 2 pi s over s squared plus 1. And we've got s over s squared plus 1. And let's go ahead and maybe write this out real quick as 4. Well, that's not a 4 in any way. 4 L inverse of e to the minus 2 pi s over s squared plus 1 plus L inverse of s over L inverse of s over s squared plus 1 is what I'm planning to write as soon as I can. Okay. Well, that thing. I can't even write an arrow. Awesome. L inverse of s over s squared plus 1. Okay, so now we have to take those inverse Laplace transforms. So the first one that I'm going to take is going to be the easier of the two. So L inverse of S over S squared plus 1. That just looks like something from our Laplace transform table. We know right away that that's going to give us cosine of t. And then the slightly trickier thing is going to be L inverse of e to the minus 2 pi s over s squared plus 1. And I'm going to need a little bit more room for that, so we'll continue on this page. And maybe things will suddenly be better with the pen on this page. It's looking like that's a no for us. Okay, so we're trying to take L inverse of e to the minus 2 pi s over s squared plus 1. And what's important to note is that this looks like L inverse of 1 over s squared plus 1 times e to the minus 2 pi s. And nothing that we've done in this class today tells us how to find that thing. We have to think back to how we would have taken this Laplace transform last week when we were learning about piecewise functions. So kind of referring back, we know that when we see e to the minus s, that tells us that we're thinking about piecewise functions. That tells us that we have u of t minus whatever's times s. For us, that's going to be our 2 pi. And we know that this right here becomes our f of t minus 2 pi. So for us, that f would be what's related to 1 over s squared plus 1. So that's a sine of t type term. So we're going to have just sine of t minus 2 pi times u of t minus 2 pi. And then we can go ahead and put everything back together. So using what we found on the previous page in this, we know that y of t is 4 times sine of t minus 2 pi, u of t minus 2 pi, plus cosine of t. And that would be our solution. And what I want to do is talk a little bit about what the solution means. So right here, this first part, cosine of t, this just looks like the undamped spring solution. If we had y double prime plus y equal to 0 and the right initial conditions, your sine of t type term would go away and you would just have cosine t. What's happening is the second term kind of kicks in after t minus, or after t hits 2 pi. So after t hits 2 pi, u of t minus 2 pi starts to appear, and we just start adding this extra sine term. So that's after the time when you just sort of push the spring real suddenly, which we describe by the delta function. And then you always have this little sine term that's kind of offsetting everything. And so in the next video, we'll go ahead and think about what delta did here. and maybe think about that on your own as we transition between the videos.